Hello and welcome to this video looking at multiple regression and general linear models. So first we're going to start with a multiple regression model, and we're going to use Microsoft Excel to demonstrate this one. Here we have a data set in the blue, and we've got two breeds of cow. We've got an Aberdeen Angus, which is a great big black animal, as a beef animal, and the Hereford, which is a nice brown, sometimes black animal, but it has this distinctive white face. But they're both important beef breeds in the UK. Now, one thing we can do with our farmers is that we can look at the outside of our cattle and judge their condition. An animal with a high condition score of 5 would be quite a fat one. With a condition score of 1, it'd be very, very skinny, and we want something in between. Actually, what's more important to the supermarkets and the processors is the fat millimeters on the back. So the back fat thickness here in that final column is important. But that requires ultrasound or requires an inspection post-slaughter. So actually, it would be useful if we can predict that back fat from the condition score that we look at directly in the animal. It might not be the most accurate measure, but anything we can do to inform that process can just save us a bit of efficiency and save us some animal handling. So here we've got the data. I'm going to just plot this with a graph in Excel. So I'm going to select the breed and the condition score and the back fat together. I'm going to put a graph in there, so insert. And it's not the line one that you might think it is, it's actually this XY scatter plot. So I'm just going to choose the first one. And here, look, we've got red spots all over the place and blue spots all over the place. We've got condition score and back fat. But it's not what we want. It's all over the place actually. And whatever you do in trying to manipulate this, I can't find a way of presenting it properly from this 3-column format. So I'm going to delete that. What works better is if you take the first one, which is our prediction column. So we're going to have condition score on the x-axis, and then instead of having the 3-axis approach, I've put the Aberdeen Angus backfats in one column and the Hereford backfats in another column. And you see how it's split like that. And if I select these data, go to insert the scatter plot, you can see here I've got pretty much what I want. I need to add the axis labels, but here I've got the Aberdeen Angus in blue and I've got the Hereford in red, and that's what I want. So I'm going to delete that because actually secretly over here I've got the graph drawn already. That's the one I want here, and you can see that here I've got along the bottom I've got the condition score. I haven't labelled that, and up the side I've got the back fat prediction. Haven't labelled that either, but moving on. Here we've got our 2 lines, and can you see that each line has its own equation? So the red representing the Hereford cows. Here I've got a line with a steeper gradient than the blue Aberdeen Angus line here, and my line, if I just take the Aberdeen Angus one, is y equals, and then 2.19, that is the gradient of the line. So 2.19 times the x value. So if the x was 2, then the value of here would be 2 times 2.19, which would be 4.38. And then I add 8.18, that's the constant, or that's also known as the intercept. That is where the blue line, if I continue that blue line down, it will cut this axis at 8.18. If the red line, which is a gradient of 3.71, which is basically 3.71 across for every one up, it cuts the axis at a lower value of 4.64. You see, it's going down and steeper, and it'll cut the axis about here. Okay, these R-squared values are basically telling us what is the quality of this prediction. How much of the variation is accounted for, and here we can see that the red prediction at 0.6 is better than the blue prediction of 0.27. Okay, so that's the overall values. Just want you to keep an eye on these values. here, because that's one way of plotting these data. But there's better ways to do that. Actually, we're going to do it with the multiple regression in Jamovi. So let's take our values. We've got our values here. And what I've done is I've copied these into Jamovi. Now I've set this all up already, so let's go to Jamovi and have a look what's already there. So we've got breed, condition score and back fat. And there they are. Breed, condition score and back fat. And actually I've added a separate one. So I had the sex of the animal, whether it was male or female, and that was from this next sheet here. So I've got the breed, condition score, back fat and the sex of the animals to see if we can build an effective model to predict the back fat of these animals. So this is the one I'm trying to predict, back fat, and we're going to do that with regression. So let's go to regression, and we're going to do the linear regression because this is all based on straight lines here. So we're trying to predict back fat. That makes it the dependent variable. So I put back fat here. And here we've got a choice of covariates or factors. Covariates are those variables that have a continuous outcome. You can see that because there's a little ruler there to tell us. And here we've got condition score. That's the only one that we've got in our continuous outcome. So we're going to take that one, put it here. And our factors, well, they're nominal. They're categorical variables. And that's with the three circles. And we can see that breed and sex are both categories, aren't they? Breed, I've got Aberdeen Angus and I've got Hereford. Sex, I've got male and female. So let's put those in the model. Factors, breed and sex. And here in Jamovi it nicely updates as we go. And there's our values. So here we have an R squared. The overall model is accounting for 0.49 of the variance. So nearly half of the variation is explained by this predictive model. Actually, we might want to improve that. If we go to our fit measures, so which is under model fit, usually that's hidden. So if I hit model fit here, I can put an adjusted R squared in there. The adjusted R squared allows for the number of terms in the model. Now I've got breed and sex in the model. The more terms you put in there, actually you're making the model more complicated, and therefore an adjusted R squared is important. So it's slightly reducing our predicted variation here. It's useful to have the f-test value as well to give an overall model test. Is this model any good or not? Let's have a look. Well, it's highly significant. It's very good at predicting 43% of the variation. That's not bad. If this goes from 0 to 1, and nearer 1 is better, but still this could be a useful predictive model. Let's look at the actual values here. The intercept, this is a sort of combination of that blue and red line that we saw in Excel. So here the intercept is where the single line of this model cuts the axis. This is sometimes known as the constant. Condition score, for every condition score of 1, we add 2.76 to the predicted back fat measure. And here with the breed, Aberdeen Angus is our reference and Hereford is our category. So Aberdeen Angus, you give that a score of 0. That's actually taken care of within this constant or within this intercept value here. But the Hereford, for a Herefordshire animal, we would add 1.49 to our predicted back fat measure. Here we've got the male as the reference level, and the male would get a score of 0, and again that's included in the intercept or the constant, and that's what this means. It represents the reference level. So all of the male and Aberdeen Angus is in the intercept, but the female has an additional 2.20 millimeters of back fat compared to the male on average, and that's our model here. Now in my example, I want to change the reference levels of one of these. I want to make the males with reference to female, not the females with reference to male. So I'm going to change the reference level. I actually have that option here in Jamovi. It's really neat actually. I click here, and here I could have changed it to Hereford if I want to. I'm going to leave it as Aberdeen Angus, but here in your handout I've got female as the option, so I'm going to put female here, and you can see it updated. Instead of being 2.2 higher, the male is 2.2 less in terms of millimeters than the female value. So there's our values here. So I can take those and I can copy those back to Excel. So I could right click, I can copy all the analysis or copy all, and then I can put it back to Excel. Okay, so here has values here, and here I've copied them in full, so I've got all the numbers. Okay, so that's our model, and this table, well, that's pretty much ready to go. You know, I could take that table, ignore the colours for a minute, so I'll come back to those. I could take that table, just those lines here, and I could copy them into a Word document and produce something that looks like this. This is the overall table that I want at the end. Here I've got table 1, multiple regression model to predict back fat from condition score, sex and breed in beef cattle. Here, there's my predictors, there's my reference values in the italics, and there's my main ones here. There's all the numbers from the table. Oh, confidence intervals, we forgot about those, didn't we? So let's go back to Jamovi. I don't have confidence in the intervals at the moment. I'm still looking at the data here. So if I click here on the table, I can go back to my model coefficients, and I can click on confidence interval, and there they are. So for the intercept, it's 7.46, but that's between 3.01 and 11.91. If I look at my condition score, we estimate 2.76, that's our coefficient, but that's between 1.45 and 4.06. And if I go back to Excel, oh sorry, go back to the Word, you can see those values here. There's my confidence intervals in the table. Okay, so that's how I get the model together. Let's have a final look at making a prediction. So I actually set some tasks here. I've set a male Aberdeen Angus with a condition score of 4. What would we predict? A female Hereford with a condition score of 5. What would we predict? So I'm going to take those down underneath here. I'm going to put them there and allow us to work from that. So let's work on the first one. We've got a male Aberdeen Angus with a condition score of 4. What would we predict the back fat? And these are the values I want in the colours here. So for the intercept, that doesn't change. So I'm going to copy that one. And so for example A, so this is example A and this is example B. And for A, I need the 5.26 because the equation is 5.26 plus the condition score of the animal plus the breed plus the sex of the animal, those coefficients. So for A, for a male Aberdeen Angus, well, they're both going to have this one, the constant. So here is the constant, or I'm going to write constant because I like constant, but the constant is the intercept where it hits the axis. Here for the condition score, well, let's make that one a bit wider. Here, condition score is 2.76 multiplied by what the condition score is in our prediction, and that's 4. So we're going to make that equals 2.76 multiplied by 4. Oh, that's 11.04. Now this is an Aberdeen Angus, and that's our reference category here. So that's already there. So here for breed, it's already in the constant, so that gets a value of 0. And here I'm asking for a male. Well, here in this model, I haven't changed it around, remember, the male is in the intercept So that's the reference level. Here, I changed the male and the female around. So notice it was minus 2.2. But here, I've got it the other way around. I've got the male is still the reference level. So I'm going to just go with that. So here, for sex, the male is the reference. So that is also a 0 here. So if I want to see what the predicted back fat is, back fat, it's the sum of all those. I can just hit that button, the sum, and it adds them all up. So that's my answer. I can make it nice and pink. So predicted back fat for A is 16.3. Nice. And for B, well, B is a female Hereford with a condition score of 5. The constant doesn't change. I can just copy that across. That's the same. The condition score is equal to the condition score estimate, this coefficient 2.76, multiplied by 5, because that's what we've got in our equation. The breed is a Hereford. Now the Hereford gets an extra premium of 1.49, so let's put 1.49 there. Angus gets 0 because it's a reference, but Hereford is plus 1.49, so we put that there. This is a female animal, and the female gets an additional 2.2, so we're going to put 2.2 there. Okay. Now I could just type sum in again, or I could just drag this formula across, which I'm going to do. And if you can see, this female animal, well, she has a predicted back fat of 22.75. You see how that works? So ultimately, let's have a look at the equation. The equation is y, or let's say back fat, let's write it out in full, back fat equals, and here, the constant 5.26 plus the condition score with an estimate of 2.76, so it's 2.76 times the condition score. This condition score. So that's 2.76 times condition score, plus, then we've got the breed, plus breed, which is either 0 or 1.49, depending on which breed it is, plus the sex of the animal. And that's our answers. There's our predictions. Now, the last thing I said is let's have a quick evaluation of those predictions. Let's go back to the data set. This is a male Aberdeen Angus. Well, we've got males and females in there. Well, that's fine. We've got Aberdeen Angus in the data set. That's fine. We've got a condition score of 4. Well, here the condition scores of the Aberdeen Angus varies from 1.5 up to 4. In fact, there's 4.5 there. We could do this with proper descriptive statistics, but there's only a few data here, so we don't need that. So that's well within the range. But let's have a look at the female. Yes, so we've got Herefords here. We've got female Herefords in the data sets, so that's valid. Condition score of 5. Well, here the Herefords, the lowest is 1.5, but the highest is only 4.5. 5 is actually the maximum condition score on a general rating. But we don't have any in the data set. We don't have anything that far. So we just have to be a little cautious in extrapolating the data beyond our measured range. Our measured range is only from 1.5 to 4.5, and 5 is outside that measured range. It's only just outside that measured range, so perhaps we could have some confidence in it. But if it was a long way outside that measured range in a different data set, we would definitely hope to increase the predictive data sets so we can therefore use that to make better predictions in the future. Okay, so what we've done is we've got our data, we've looked at 1, 2, 3, 4 different terms. We've used 3 different terms, some of them categorical, one of them numerical, to make a prediction of a numerical outcome. That's at the heart of the general linear model. Here's our findings, and this is how we present it, with the table, with our constant or intercept, with our different variables. There's the the covariate one, which is a continuous variable. Here are two categorical variables with their reference figures, and we make sure we have a proper title. We make sure that we have details of the model overall significance from that f-test with our adjusted r-squared, with the number of individuals in our sample. We also make sure that the intercept represents the reference level. We have that nice footnote there. We have a standard error figure here. We have our lower and upper confidence intervals here. And here we have our individual t statistics that tells us that condition score is significant in this model. Breed is not significant in this model, but it might be useful to include it. The sex of the animal is a tendency of 0.10, but it's not significant in the model overall. But together they give us an adjusted r-squared of 0.49. And that's pretty decent when trying to make predictions in this world. Thank you for watching this video about general linear models and multiple regression.